Hello everyone, I will be presenting our work Material Phase Prediction for Lithium-ion Reconstruction using Hierarchical Curriculum Learning. My fellow collaborators are Dr. Nikhil Molidhar, Dr. Ramakrishna Kannan, and Dr. Shrikant Allu. And this is a collaboration between computer scientists and battery researchers from Oak Ridge National Laboratory and Stephen Institute of Technology. Lithium-ion batteries are advanced energy storage technology, which has wide range of industry applications. Examples, laptops, smartphones, electric vehicles, etc. The figure is showing a lithium-ion electrode consisting of cathode and anode. The movement of active materials like lithium and manganese present in the electrode and their distribution influence the flow of electricity, and hence they can impact the change in the battery cycles and also the battery degradations. But the current X-ray nano imaging techniques, they are able to collect and analyze the distribution of such materials from the cross sections of the electrodes. However, they are very time consuming and also costly. The existing X-ray microtomography imaging techniques, they often even, which are a little lower in cost, inexpensive, but they are often suffer from low contrast and low resolutions. Now, figure A is an example of a low contrast tomography image that is that has been collected from a cross section of a small portion of the cross section of a battery electrode. And none of the active or the binder materials, or like the lithium, nickel, carbon, or the pores, they can be identified or perceived from this. Neither even the material phase boundaries. The change of intensities, which is showing a little bit non-smoother over the image, that might represent the possibilities of some material phase boundaries here. But however, it cannot be perceived. And if we use a image segmentation model, which has been widely applied for different computer vision applications, we can identify the material phases, and that been shown in figure B. However, the predictions within this red box can still lead to many small artifacts, that is, many small noises, and they are very irregular in shapes, which is not desirable. Now, these minor artifacts can eventually lead to a high error in 3D reconstructions, and they cannot aid in understanding the battery mechanisms. Hence, we need a model which can enable the learning the fine-grained representations for reducing these artifacts in the predictions. And our model eventually needs to automatically enable to distinguish these predictions, which one needs fine-grained representations and which one need coarse-grained representations. And we want to develop such model. We pursue a curriculum learning technique, which is basically a strategy to how to train the machine learning model in the order from easy to hard data sets. And in our case, such easy and hard data are basically the pixels of low and high degrees of difficulty. By low and high degrees mean which need coarse or fine-grained representations. Now, if we see the last figure, it is actually showing the predictions based after incorporating the curriculum strategy. And if we see the most of those artifacts, which has appeared in figure B, they have already disappeared. Now, our overarching goal for such task is basically first to identify the material constituents towards reconstructions of the 3D electrode from low contrast tomography images, and also eventually identifying the materials with very low prediction errors, because the low prediction errors can aid in calculating the physical parameters, which is very important eventually to understand the influence of battery performance. And our contributions are, we develop an uncertainty framework to predict the material phases of electrodes. We introduce hierarchical curriculum learning techniques for identifying fine-grained material phase boundaries, and we develop a model to capture local and global representations of fine-grained phase boundaries. To our knowledge, there is no such existing technique available at present in terms of battery modeling literature, which can identify the phase boundary from low contrast tomography image. And so first, our hierarchical curriculum learning strategy, which we define is basically as a set of ordered strategies, which can partition the data sets from easy to hard. And each strategy here is harder than the next one of the order by some measure of complexity. Now, using such hierarchical curriculum strategy, our proposed architecture is basically using first strategy. Let's say example, first using strategy S1 can eventually partition the data sets full D into easy and the hard data, D1 and D2, where the easy ones are basically to be trained with a global model, which to learn the coarse grain representations. And strategy S2 is to be enable the local model for learning the fine grain representations. Now, our problem of material phase predictions thus consists of a set of tomography images where we need to predict the material levels per pixels. And our idea is to predict such materials for unlevel tomography image. So we mapped our entire problem as image segmentation task, and our first attempt is to pursue a Monte Carlo unit, as the unit has been widely adopted in the biomedical literature segmentation, where it has been able to capture very nuanced variations as well. And the figure in the right, it shows an example of the predictions from using such unit, where we see the false predictions are mostly the red ones, and it has lie mostly around the material phase boundaries. So this eventually leads us to follow an assumption that is the high uncertainty values by the global model, they tend to give more incorrect predictions. And this high uncertainty can be quantified as entropy values using the dropout. And now our first curriculum learning strategy, that is coarse grained curriculum learning, HCL-IDK, is basically to leverage the coarse grained model to partition the data sets. Now, the figures, this shows the prediction probability of each material class per pixel obtained by the global model. And the blue values are showing the high probability class for that pixel, and the white or the more neutral values that are mostly at the phase boundaries. This leads us to a second assumption, that is average prediction probability of global model for incorrectly predicted pixels bears similar weight. Now, to automatically enable the HCL coarse grained curriculum learning strategy, eventually which can partition the pixels based on the two assumptions, we aim to build a 5-step binary classifier that can classify the incorrectly predicted pixels as an I don't know class. Next, we want to develop a local model that is LCGAR to learn more fine-grained representations for each of these I don't know pixels that has been classified by our coarse grained curriculum strategy. Now, we leverage CNN architecture here for the local model. But the unique feature here is to capture the local properties using the for each IDK pixel using such architecture. And for that, we designed our input channel to consist of not just the local image surrounding the target IDK pixel, but also using the global model output features, that is the predicted class levels of each target IDK pixel, and also the prediction probability that has been obtained by the global model for each of these IDK pixel. Now, this figure is showing our proposed overall framework MatPhase, where the low contrast tomography image first trained through a global model to obtain the coarse grained predictions and uncertainty map. These uncertainty maps and the prediction probabilities then pass through a curriculum, coarse grained curriculum strategy, HCL-IDK, which is basically a binary classifier. And hence they identify again the pixels, the I don't know pixels. The idomopixels then are passed through a fine-grained curriculum strategy, which ordered each of them again from easy to hard datasets based on the uncertainty maps. This order is to train the local model based on the input representations. And finally, the aggregator model selects the final predicted class obtained by the global or a local model. Now, as an experiment for evaluating the performance of MatPhase, we want to pursue 3 research questions. First, is hierarchical curriculum learning even effective for modeling smooth material phase predictions? Second, does incorporate global information in local modeling? And third, how does MatPhase perform over the state of the art? Now we want to evaluate each of these questions across multiple metrics, which has been already well known for image segmentation and classification tasks. Now, first, for answer how our whether our if our hierarchical curriculum learning is even effective, we designed 2 variants for based on our MatPhase framework. And the first one is basically a global model, which does not use any curriculum strategy. Second one is obtaining predictions by only removing the fine-grained strategy, that is HCLUI, but keeping still the coarse-grained strategy, it's CLIDK. And the third one is obtain the predictions using all of the curriculum learning, basically our MatPhase framework. And we observe that our framework performs 4 out of 5 metrics. Next, for answering question 2, we want to evaluate the importance of global model features for local modeling. And for that, we design the different variants of local model by varying the input representations. And again, we see MatPhase performs all other variants. Now, the final question is we want to evaluate MatPhase against different baseline models. And for that, we choose the different state-of-the-art image segmentation models, as our framework is already motivated from segmentation. And also, we strategically design some of the non-trivial models using the different pre-trained modules of MatPhase. And details about the state-of-the-art and these non-trivial model designs, you can find it in the paper. And to summarize our points, now first time in the literature, we present a novel framework to predict fine-grained material phases from low contrast images. On average, our framework increases performance up to 8.5% against state-of-the-art. And finally, our framework can be a practical application to battery researchers, which eventually for understanding the material phase distributions from noisy data. And hence, they can enable modeling battery degradation mechanisms. Thank you. You can find all the code and data available at our following GitHub link.